Hello and welcome to part 2 on how to design a chemistry from the ground up. So in this particular video we're going to talk more about additional reactions and species. So far we've constructed a chemistry set including relevant ions and ground state neutral particles, as well as the basic electron collisions and ion-ion recombinations. So in this video we will now have a look at the effects of heavy particle reactions and some additional electron collisions. Note that we do not have examples for all types of reactions, as their efficiency depends on the process parameters and not all showed a significant influence under our chosen parameters. In charge exchange collisions, the charge from a positive ion is transferred to a neutral particle. There are two types, symmetric and asymmetric. In symmetric charge exchange collisions, the charge is transferred from an ion to its neutral counterpart, for example, from O positive to O. Obviously, these kinds of reactions do not change species densities directly. They do, however, contribute significantly to the neutral gas heating and can therefore change the densities indirectly. They can also influence the shape of the IEDFs at surfaces. In asymmetric charge exchanges, the charge is transferred from an ion to a different neutral, sometimes in combination with dissociation or transfer of atoms from one collision partner to the other. A well-known example of this is H2 positive plus H2, which makes H3 positive plus H. Apart from contributing to the neutral gas heating, these collisions also directly change the relative ion densities, as can be seen for our O2 case in figure 11. The recombination of atomic ions is negligible under low pressure conditions, as this is actually a three-body process. However, this is not the case for the dissociative recombination of molecular ions, such as E plus O2 positive, making O plus O, which are quite efficient. As they give an additional electron loss channel, they can influence both electron density and temperature and indirectly other parameters. They can be negligible at low pressures and in highly dissociated plasmas, but when in doubt, they should be included. Negative ions can not only be destroyed by ion-ion recombination, but also by electron detachment. In this process, the excessive electron is stripped from the ion by an electron or a neutral particle. For example, E plus O negative makes E plus O. This reaction reduces the electronegativity of discharges, as can be seen in figure 12, where we added the detachment of O negative by electrons and O to the reaction set. The direct influence on the neutral density is usually negligible, but the reduced electronegativity can influence the electron temperature and other species densities indirectly. Ion-ion recombination usually refers to the reaction X positive plus Y negative, making X plus Y. However, it is possible that one of the ions get dissociated in the process. For example, XY positive plus Z negative, making X plus Y plus Z. Such reactions are known for a couple of fluorocarbons. They have the effect of further reducing the density of negative ions. The influence on the neutral densities is rather negligible. In the comparison of the CF4 chemistry with radical losses at the walls and the O2 with chemistry without, we have already seen how the interaction of neutrals with walls influences the density of dissociation products. However, neutral particles can not only be lost at walls, they can also form there. For example, O can recombine to O2, F to F2, CF to CF2, etc. Note that this can introduce new species to a chemistry, such as F2 in CF4 discharges. If the amount of reactive species is large enough, wall recombination can have a significant impact on the plasma composition with all its side effects. Different electronegativity, changes in electron temperature. Radicals can not only recombine at walls, but also in the gas phase. These processes are highly dependent on the pressure, as they are usually three-body processes. Hence, they do not have a significant influence in our O2 example. The rate coefficients can vary strongly depending on the involved species. A rough thumb of rule is the larger the involved species, the higher the rate coefficient. So the recombination of two atomic species is less likely than the recombination of one atomic with one molecular species, which is less likely than the recombination of two molecular species. Before deciding whether to add these reactions, you should compare its expected rate with the one of the opposing dissociation reaction. In general, these reactions have the same effect as losses and recombination at the wall, reducing the degree of dissociation with all its side effects. Please note that such reactions can form neutral particles larger than the feed gas, such as C2F4 in the CF4 discharges. There is a plethora of other possible neutral-neutral reactions, typically a transfer of specific atoms from one molecule to another. Going into detail here is beyond the scope of this tutorial, as the reactions can alter the neutral composition of the plasma significantly. They should be thoroughly researched. A rather well-known example is silane. The dissociation yields primarily SiH2, which is then quite efficiently converted to SiH3 by reactions between neutrals. Also note that in the mixed discharges, such reactions can produce new species, such as COFX in the CF4/O2 discharges. In the O2 case, the metastable O2 states can, for example, detach electrons from negative ions quite efficiently in contrast to ground state O2. As figure 13 shows, this leads to a reduced density of O negative. Note that we also included the wall losses and recombination of O in this model to achieve sufficient densities of metastable O2. When deciding whether to include excited states or not, you should get a comprehensive overview of possible reactions they can induce and estimate their rates in comparison with the ground state reactions. When in doubt, include them. So far, we have neglected excited states and only dealt with neutrals in their ground state. However, excited states can have a significant impact on the discharge. Possible effects include many rates, including neutrals, are higher for the excited species, so they can have a significant influence despite their smaller densities. Excited species can also induce or accelerate surface processes. Fluorescent states emit photons, which can also induce surface processes. Excited states can ionize neutrals if the excitation energy is higher than the ionization energy of the collision partner, pinning ionization. Through collisions with electrons, excited states can affect the shape of the EEDF, electron temperature, and rate coefficients. This tutorial was aimed to show you how to design a chemistry from the ground up with gradually increasing your model's plasma chemistry complexity using two examples. A link to a PDF with all this information will be provided in the description box below. Tools used today were QDB. To find out more about this, visit our website at www.quantemoldb.com. QVT Plasma Modeling Software.